Hi there, future Ps. This is Wasim Asgar. I'm a licensed professional electrical engineer in the US and Canada. I have authored several books on the topic of FE electrical and PE power exam preparation. And I also run popular exam preparation programs for FE electrical and PE power. In this video, I'm going to go over a few questions that my students asked me regarding NFPA 70E during PE power live training. NFPA 70 is an interesting standard. It has been getting a lot of attention over the last few years because of increasing safety awareness. Generally, it is considered to be the arc flash standard, but in reality, the scope covers a lot more than just arc flash. There's some interesting calculations in NFPA 70E which strictly speaking don't even form part of NFPA 70 because they're part of the Annex D IEEE 1584, but these calculations get a lot of attention from students because they're numerical. We as engineers like to do numerical problems, plug and chug if possible. You'll see me pointing out several pitfalls in this video when you're going through these calculations. Despite that, I find students repeatedly making silly errors on these calculations. Before we jump into the content, I would really appreciate if you could like this video and subscribe to the channel if you haven't already done so. On a weekly basis, I'm creating content for FE electrical and PE power exam preparation, as well as on other topics related to power systems engineering. So without further ado, let's dive into the content. This question is actually a three-part question that I received from the student. I typically feel that an open-ended question like this tells me that the student hasn't put in the necessary time and effort. But since we have time during this training session, I am more than happy to go over this in detail. So the question is, hello Asim, can you please go over these problems during office hours? And this is a three-part problem series, 3.3J, 3.3K, and 3.3L from the study guide, second edition. Okay, so the first problem, 3.3J, is I've reworded this to actually, present it in a little bit more easier to follow, easier to understand manner. In fact, one of the key steps in solving any complicated problems is to paraphrase it in a way that you can approach it more systematically. Okay, so over here, the question 3.3J from the study guide second edition is saying that calculate the three-phase arcing fault current if arcing time is 0.1 second. Now in the actual problem statement, I have not presented these details like given voltage fault current is equal to 30 kA, voltage is equal to 0.480 kV, and conductor gap is equal to 25 millimeter. Okay, now I have labeled them properly as close to how they appear actually in the equations, right? And used the units of measurement consistently, right? So that I won't have any issue in plugging these parameters into the equation. And trust me, putting this given information in the format that I've presented you is actually part of the solution that you are expected to do. Is it making sense, guys? Okay. Remember what I told you about the units of measurement? Why did I not write this as 480 volt? Why did I write this as 0.480 kV? Is something very important over here. Why did I not write this as 30,000 amps? Why did I decide to write this as 30 kiloamps? Because the equation needs you to use these UOM. Exactly, Chris. All right, guys. Now, if you are thinking that, okay, on the exam, if a question shows up, I have an idea of where, IEEE 1584 is in NFPA 70E, and push comes to shove, I'm just going to pull up that section. And in fact, they've also done some sample calculations for me, which is fine. But if you have not done these calculations by hand yourself, either using, my resources or anything else, right? Within the program, as you guys know, I've gone through these practice problems several times within the lectures, quizzes, mini exams, homework assignments, live training, study guide, right? Now, those of you who have worked through this, you know automatically that I am not going to make this mistake. This is a potential landmine, correct? Now, these things sound very simple, but out of the options A, B, C, D, I can very easily, create a solution and an answer taking this approach forward and presenting you with one of the solutions that one of the answers that would match this particular route. And exactly as you were saying, Ariane, these calculations look very easy. Okay. And the reason why I'm willing to sort of cater this or handle or field this particular question, which is very open-ended, right, is because, it gives me a little bit of points to reinforce and hammer. Okay. Otherwise, this type of open-ended question, Wasim, can you solve this again? I think that you need to put paper to pen and actually work through this yourself. You can look at these solutions, all day, all night, and get a warm and fuzzy feeling that come the game day, I'll be able to make it work because it's just math, right? And my response to the student was that it's really just the math where you fell short, right? Okay, so I presented this in a way. I basically chewed the question, right, and paraphrased it such that I can deal with it much more comfortably. Okay, so I would say the level of difficulty of this problem, hypothetically, let's say we have 5 levels. Let's say this was level 5, although it's not a level 5 question, right? It's just, I would say it's a medium level difficulty problem at best because you know a clear path on regarding how to solve it. But let's say it's a level 5 problem, right? Just by presenting the data in this particular format, you've actually reduced the level of difficulty at least by a couple of notches. Do you guys agree with me or not? Right? We've, in the very first step, made it 5-3, right? Because now if I go give this to a first year engineering student, right, along with the equation that I'm going to present right now, I would say that more than 80% of the students would be able to plug and chug. And if you struggle to do that, then you really need to pay attention to details. Okay? Because the P power exam, on a spectrum of level of difficulty, these questions are what I call as popcorn questions. Okay? Let's move on, guys. So determining the value of K, I'm commenting that, okay, there's one more parameter, K, that shows up in the equation, and we need to determine the value of K. So in my response to the student in the email, as I K is a constant used in the arcing current formula that depends on the type of enclosure. And what did the problem statement tell you? In the actual problem statement 3.3J, we know what the type of enclosure it is, right? This is for arc in a box, such as MCC and enclosed switchgears. Okay, and the value of K for this is minus 0.097. How easy is that? Now, if you randomly choose K for an open box versus an arc in a box, I mean, that tells me that you're not competent enough, that you haven't invested the time and effort to actually figure out these calculations, right? And in my humble opinion, as compared to somebody who has put in the time and effort, you don't deserve a point on this question. I think that's just fair, right? So this value is selected based on empirical data and reflects a specific characteristics. So for all practical purposes, the number that we are interested in is 0.097, but with a negative. Okay. Now from this point onwards is all plug and chug. But plug and chug will only work if you actually use the correct UOMs. If you actually left the voltage as 480 volt and decided to use 480 instead of 0.480, as we discussed earlier, you are going to get incorrect answer. Okay, now you can argue all day long that Basim 0.48 kV is basically the same stuff as 480 volt. So why is it not working out? Well, it's not working out because the formula is to be used in a particular manner with a particular set of units of measurement. Is it correct, guys? Yeah, and then other variations could be that you may actually start from line to line voltages, right? So you have to be very careful about how you're interpreting this. So the phase voltage, right? So this is line to line voltage. So they may give you additional details about delta or Y, right? So in that case, you'll have to stop a little bit and think about if the line to line voltage is given to me for a Y network. Okay, sorry, if the phase voltage is given to me for a Y network, Is it the same as the line-to-line voltage? It's not. The line-to-line voltage is the same as a phase voltage for a delta, correct? So good point there. Yeah. So you need to take some time and pay attention to what is relevant, important, and what is not. Okay. From this point onwards, it's simple calculation, guys. Just be very careful. And the student actually made mistakes apparently in the math. Okay. So making mistakes in math is, in my opinion, a fatal error, right? Because that is like throwing points away. Okay. That's like burning cash, or like Mr. Beast throwing boatloads of cash on a freeway. Have you guys seen that episode? Mr. Beast. You guys know Mr. Beast, right? No? No one knows Mr. Beast? Yeah. Yeah, he creates these viral YouTube videos. In one of the videos, he actually threw $100 bills or something like that, boatload of cash on a freeway. But don't waste time. Don't waste these simple problems. Okay. Look it up when you guys get a chance. Mr. Beast, free cash, and whatnot. He does a lot of interesting stuff. He's apparently the biggest YouTuber right now. Okay, and then you have to take anti-log. Also remember, this is log base 10, and we are after the actual current, not log base 10 of IA. We are after the actual value of IA. So very quickly, what are the common mistakes? I pointed them out along the way. Incorrect voltage units, not converting the voltage to kV, okay? And similarly, if I give you 30,000 amps, you have to convert that into 30 kA. Misinterpreting gap and voltage constants. So we have to extract the values for the constants based on the scenario that is given to us. Incorrect exponentiation, right? And logarithmic error. So they basically go hand in hand. When you are applying the exponents, or when you are going from log to exponent, just make sure that you handle it properly. Assuming constant values, misinterpreting empirical constants, leading to errors in calculating arcing current, right? So this is similar to this. Okay, there are multiple ways still where you can go wrong. Any further questions on this? Was this helpful? System voltage levels, yes, I agree. So the phase voltage, the line voltage, okay, interpreting that incorrectly. Any follow-ups? Was it helpful, guys? Okay, 1 kV and above. Okay, there are two different formulas. Thanks a lot for mentioning that. Is it 15 kV or 1 kV, Chris? Can you please let me know? 1 kV. Okay, there's a threshold. There's a different formula for 1 kV, and there's a different formula, sorry, above 1 kV, and there's a different formula for 1 kV and below. Sorry, 1 kV and above has a different formula, and below is different. So the reference is, thank you, D4.2B, for those of you who are interested. If you like this video, then please don't forget to subscribe to this channel. Feel free to ask me any questions in the comment section of this video below. You can find tons of success stories of my FE Electrical and PE Power students over here. And if you want to learn more about preparation of FE Electrical and Computer exam and the PE Power exam, then check out these playlists over here. Thanks for watching, and I'll see you soon in the next video.